Okay, hi guys. So in this lecture, we will be discussing sulfonation. Okay, so let me write down the topic first. Sulfonation. Oops. Okay. So let's say we have a benzene ring, and we are passing concentrated H2SO4, and we have a mixture of SO3 and H2SO4, which is called oleum. We are passing it as a reagent over the substrate benzene. So what we get is something like this. This is called benzene sulfonic acid. Let us look at how does the mechanism take place behind the scenes. So we have something like a benzene ring. Now what actually happens here is um, we have SO3 also present in the mixture, and hence electrophilic addition reaction takes place here. Electrophilic substitution reaction takes place here via the breaking of this double bond and the adding of this SO3 group. Okay, rather SO, this bond will break, this SO and O bond will break itself, and the oxygen will get the negative charge, and we have something like this here. Now what happens next is, from the H2SO4 molecule, this oxygen actually attacks here and gets itself a hydrogen from the H2SO4, which is acidic, and as a result HSO4 is formed in the reaction. What this HSO4 does is, again, it acts on this hydrogen, and it removes it, creating a negative charge here, and thereby forming a double bond, and thereby this carbon atom forms a double bond with the neighboring positively charged carbon atom. So we have something like this formed. Okay, and obviously H2SO4 is released. So this is the major product formed in this reaction. Okay, so as we have seen that kinetic isotopic effect, um, wherein when we discuss what will be the rate of reaction when we actually replace benzene with C6H D6 and C6T6. So as the redetermining step uh, does not involve the C and H bond, hence in all the cases rate would be the same whether we looked it in the case of nitration. Okay, in the nitration side, yes, all the rate of nitration would be same, but in case of sulfonation and iodination, what we find out experimentally is the rate is surprisingly of the order of this. Although there is not much difference between the rates, they are although comparable, but still this is the general order. And although in its RDS also there is no involvement of the C or H bond or C or D bond or C or T bond anywhere, because we are just adding the electrophile to the phenyl ring, but still some other external or indirect factors are there which influence the kinetic, which influence the rate of sulfonation, and hence the kinetic isotopic effect can be seen in sulfonation and iodination. Okay, let us look at another example where we have a benzene ring. So just first let me write an example where we have summary of what actually happens. We have H2SO4 at 50 degrees Celsius. Obviously SO3 gas would be present here, and the mixture would be known as oleum. This is the reaction which we looked at. Okay, and what actually happens if we um, heat it at 150 degrees Celsius and provide it some uh, dilute acidic medium. Okay, so what actually happens in that case is desulfonation happens. In other words, this benzene sulfonic acid again converts back to benzene. Okay, so this is called benzene sulfonic acid, and this method is called sulfonation, or rather desulfonation. Okay. Okay. Now let us look into the mechanism of how this desulfonation take place. So as I mentioned that we are taking a dilute acid so that our benzene sulfonic acid can act as a acid here, and let's say I have this as this dilute H plus concentration, which will act as a base. This will act as an acid. So what will happen is this O and H bond will break itself to create a negative charge here. So what we will get is something like this, and with H plus here. Now we heat this again at, as I mentioned, 150 degrees Celsius, so as to break this bond between carbon atom and S atom. So what actually happens is we actually break this bond, and with the release of SO3 gas we have a carbanion formed, something like this. Okay, and this carbanion actually acts again on the H plus, which was released in the previous step, to form or restore the benzene ring. So with this we complete the mechanism of desulfonation. Okay, so let us see another example. So let's say we have something like toluene, or we have at para positions relative para positions, and we have SO3H and CS3 group, and we reacted with Cl2 in presence of AlCl3. So what would be formed in this case? We would have something like, from the two Cl, one Cl would be attacking on AlCl3, and other would be getting a positive charge. Okay, and this positively charged chlorine would be attacked by the phenyl ring as a electrophile, and what we will get is, as a result, this is a plus M group, this is a plus H and plus I group, and this is a minus M group. So obviously Cl would be attached to the ortho position of activating group, which is CS3 in this case. We would get something like Cl here, and obviously double bonds here, and SO3H here. What would happen next is, obviously you are providing some heat to the sample, to the reaction, or to the product, and we'll get something like, obviously there was a positive sign here, the plus, the carbon and H bond would be broken to restore the benzene ring, and the H plus would be released. Okay, so we will have the final product as Cl here and SO3H here. Okay, and what happens if we again react this with in acidic medium, and we heat it again? Desulfonation of the ring will take place, and we will get finally something like this as our final product. Okay, so with this we come to an end of this lecture. In the next lecture we'll be seeing some more examples, and we'll be seeing elimination intramolecular. Okay, till then, good luck and goodbye.